Hello, everyone, and welcome to our webinar today, Linear Pluggable Optics, the low-power optical interconnects for AI and hyperscale data centers. I'm your moderator, Sean Buckley, Editor-in-Chief of LightWave and BTR. And before I begin, I want to thank our sponsor, Keysight, for making this webinar possible today. During today's webinar, we'll review the important technical differentiators found in this emerging interconnect field and how the electro-optic interoperability and testing methods are being addressed to satisfy cutting-edge system interconnect performance needs. Just wanted to make a quick note that Keysight is currently holding an LPO interop event in Santa Clara, so you're getting an up-to-date, webinar with lots of action going on to drive this industry segment forward. But so let me just I'll quickly introduce today's speakers. We have three experts in LPO and optical technology: Dr. Edward Flan, Senior System Architect for Signal Integrity Products Group of Centec; John Calvin, Keysight Strategic Product Planner for High Performance Networking Technology at Keysight Technologies; and Hadrian Luchette, Vertical Lead for DC Networking at Keysight Technologies. Three great speakers. But before I hand things off to our speakers, let me quickly review our webcast setup. For those of you who may be joining us for the first time or for the first time in a long time, I'll start with the Ask a Question box you see near the slide area. I invite you to feel free to ask questions at any time during this event today. I'm sure we'll get a lot of them. To submit a question, just click in that box, type in your question, and hit the send button. We'll address your questions after everyone's finished their presentations. And if you run into a technical issue, just feel free to reach out to our webcast technician, Milan, and she'll be happy to help you out. Next, if you know someone who might benefit from seeing this webcast, or you just want to revisit the presentation yourself, the event will be available on demand from our webcast archive on our website for several months. We'll send you an email with a link to the archive sometime in the next day or so that you should feel free to forward to your coworkers. And the archive version of the webcast will also be accessible from the webcast archive of our website, which you can reach via our homepage at lightwaveonline.com. If you'd like, you'll also be able to download a copy of today's slides via the Event Resources tab. You should see on your screens right below the Ask a Question box. Just click the tab to reveal the slide file PDF. And with that, I say let's get started. I'm handing it off. Okay.
Okay, welcome everyone. So I'm Ed Furlan, System Architect for Semtech up in Ottawa, Canada, and I'll be providing the introduction portion of this talk today, the webinar today. So I'll be giving a high-level overview of LPO optics. So just stepping back a little bit for people that might not be aware, so different as far as 100 gig per lane optical modules go, it appears so the industry will have various options for different styles of modules. So the module shown here on the right is the industry standard way of modules being retimed today. So what we have here is what's been around 25G NRZ, 50G PAM4, 100G PAM4, where we have retiming in both directions of the module. So if you imagine a host switch here on the left, signal comes in, there's a DSP retimer, and that drives the optics out into the transmit side, into the fiber. And similarly, on the receive side, we have a retimer on the receive side. So any optical impairments, the signal gets transformed to an electrical signal, and then that DSP receive portion here gets rid of the impairments and sends a clean signal out to the switch. So this is the way the industry's been. And what's happened in the industry now is basically the power of these modules. So there's a bubble above each box. So if we take the situation for, these are just approximate numbers, but an 800G single mode module today with a DSP, consumes about 15 to 16 watts of power. And the industry's has started to look aggressively at minimizing power. So one of the ways one can imagine doing that is taking this, removing the DSP function and just taking the signal directly from the host side. So the highly digital DSP function disappears and the signal into the module from the left-hand side here just goes through a linear chain. So a filter, an amplifier, and drives the optics. And similarly in the receive side, again, it's a full analog chain. So where, as I said, typically we're looking at 16 watts. If we look at implementations, production modules today for LPO, you cut the power in half, so you're down to 7 to 8 watts. And then also, this is sort of the most aggressive power drop that you can have. As well, there's work in the industry in OIF, as saying for linear within OIF. There's a lot of work in the industry on an RTLR type of function. So this is a half retimed function. So you can think of this box in the middle here. This module takes half of the concept of a full retimer. So the DSP TX migrates into the transmit path of an RTLR module, and the linear concept of the LPO migrates into the receive path. So you have some goodness from LPO, and you have some of the DSP retiming aspect in the transmit path. So the key thing is here, this work was started in OIF, Optical Internetworking Forum. This work also, so what happens is now in the industry for 100 gig, there will actually be various solutions that the implementers and system operators can actually leverage. Depending on network needs, you can go full retimed, you'll be able to go half retimed, and you'll be able to go full LPO. So the key thing here is LPO, obviously, since there's no retimer here, the demarcation point that you had for DSP is gone. So as the bullet here mentions, a key aspect of these types of systems is to control signal integrity. It's crucial, and how the switch equalization is done in the switch is important. Just quickly moving on to the next slide. So this is to cover off acronyms. There's a lot of acronyms in the industry, and I just wanted to kind of highlight for people the work that was started in OIF linear. So the actual specification for N-lane 100G is covered by this specification in OIF. This should be ratified this year. So CEI 112G linear PAM4. And what the OIF specifies, if we take a representative linear module, and if people aren't aware, so the electrical interface is your TP1, TP4. So as I said, the signal from the host switch comes in at TP1. This is electrical, comes out optical, TP2. This is your transmitter. You're here on the fiber. You come back TP3, TP4. So OIF has specified TP1, TP4 electrical interface specs, and that's what's contained in this document. And then the methodology is, if this has been done correctly, and depends on what PMD the module implementer wants to implement, that references back to IEEE. Let's say if it were an Ethernet client type module for data center, IEEE 802.3. So here it could be a 400G base, SR4, DR4. So multi-mode or single mode optics. And so the OIF spec does the aspect here. It specifies TP1, TP4, and the optical interface is leveraged from the existing IEEE specification. So this is the situation today for 100G. The industry has also kicked off now a 224G linear. So a lot of the methodology and way of doing things from 112G is being carried over into 224G. So this is a future project. The other main thing that's going on in the industry is there is an LPO MSA consortium group. Basically, that work will be specifying an optical module with a new PMD. So that initial LPO MSA is called 100G DR LPO. Now that industry consortium specification works off of the OIF spec, the electrical, and what it does is basically extend the reach on the host side to a full VSR, kind of 16 dB. And then also, as I mentioned, for OIF, the specification here is slightly modified. So what LPO MSA does is it touches all of these interfaces here. Key thing, just to walk through an LPO system, we don't have time today to go through the details, but again, the main aspect is it's an end-to-end system. There's no retimers, so this is a full analog system. We have the optical block here on the LPO, the transmit and the receive on the right-hand side. The key aspect is it leverages the KP4 FEC that's present in host switches today for Ethernet, and the specification is to be less than 2 e to the -4 on the bit error rate. So the key thing here is, as we walk from left to right here, the electrical signal out of the host, basically what OIF says is a signal migrates from left to right. We have a test point here, an internal test point, and it's really the equalization between the host transmitter FIR settings and the CTLE is, so the demarcation point for an LPO would be at the TP1A. The requirement is to meet all the TP1A specs. And once the LPO system has been correctly configured, so you would have configurations for short, medium, and long host electrical channels. But once this is correctly configured, then the electrical signal has been dealt with up to the TP1A point, and then the module implementer takes the electrical signal and does what he has to do in terms of signal swing to modulate whatever optics he's using, whether EML or Mach-Zehnder modulator, whatever the case might be. And again, TP3, TP4, it's the same principle. And everything on the receive side, most of the equalization gets done within the host receiver. So this is just some of the detail around TP1A. Again, Keysight and John and Adrian will go into the details. But as I said here, the key aspect is really that what we're saying at the TP1A point, it's the combination of the host transmitter FIR in conjunction with the receiver CTLE in the driver IC in the LPO module. Those two are working together to equalize the channel up to this point. So the transmitter FIR largely deals with the precursor taps, with the precursor response, and the CTLE deals with postcursor. And so if that thing is well equalized, then what happens is the signal going forward to drive the optics will be in a very good state. Key thing here is that the way a channel is judged is with a reference equalizer. So all of the standards have different equalizers. This equalizer is a 5-tap FFE, and really it's only dealing with postcursors. So as I said, precursors here, CTLE, and then we judge the robustness of the signal using 5-tap FFE, and so there's specs around that FFE that are captured in this box here. The key point here is that once the TP1A requirements are met with these OIF specifications at the TP1A point, then it puts the signal in a good framework to be able to successfully drive the optics and meet the TP2 spec. So the key point here is, as I said, it's the burden of equalization in the transmitter side is largely done with the host transmitter FIR, but it needs to be correctly configured in conjunction with the receiver CTLE. The other thing is there's new industry metrics. Again, Keysight will touch on this. In optical world, it used to be TDEC-Q. There's an EECQ metric now, so it's no longer a vertical eye closure, eye height. There's these two new metrics. Keysight will delve into that in a bit more detail. For reference, we have a similar situation here at TP4, TP5. Don't have time today to delve into this, but if people see my email and they want to contact me, no problem, we can discuss this. Or I'm sure Keysight also would be available to discuss some of these details. What I can say is OIF does a lot of good work. So really, if a company is a member of OIF, then you get to be involved in all this stuff. And that's probably the best way to get up to speed on these different applications and standards. The last slide is just to say that this work was started a few years ago, so the industry's advanced quite a bit. What we're showing here is actual bit error rates on a system with production switches. What is shown here is a 400G SR4 module. So this would be kind of your end-to-end bit error rate. So you can see that they're kind of hidden here, but if people recall, the expectation was we want to be less than 2e to the -4. And you can see here in the bullet that it's actually 7e to the -10 as the error rates. This is for a multi-mode module. And the picture shows here a short electrical channel. So this is a module, case temperature cold, then a hot, and people can see that the bit error rate doesn't degrade. And same on a long electrical channel. So this would be your 16 dB, let's say that the LPO MSA has, and that again shows the situation here. The main thing just before I hand off to Keysight, is to emphasize that once these settings are defined in the transmit, FIR, and the CTLE, there's no requirement for the module to start changing things or for the host switch. So these measurements were done with fixed settings depending upon channel loss, but nothing was changed on the transmit FIR or the CTLE. So just wanted to state that at this point, the industry kind of has quite a robust solution for LPO. There are some trials now, and it looks like the industry is trialing LPO systems, and some of the details of how these systems would be deployed is being investigated. Thanks, everyone. Handing off to John.
All right, thank you, Ed. And good day, everybody. I want to continue Ed's thought here on the OIF and how it's been a really an institution here that's been instrumental in advancing the measurement science here as we move up to higher speeds. OIF was one of the first technology groups to embrace 224 and now 448. So it's one of the more progressive areas where activity is forthcoming here related to rolling out this technology. Hadri and I will talk about the linear validation here of LPO systems. I will talk about the first two, which is TP1A and TP2, and then Hadri will get into the receiver impairment and receiver profile of testing. Similar to Ed, I like to have a family tree just to orient people on the nature of this family of technologies. Starting on the far right here, you see our 224 gig linear project, which will kicked off last November and is making good headway. On the left, you see the CEI 112 gig linear project, which was kicked off in 2021, of which we've had, I think, 8 interops, some form or fashion related to this technology. Let me just double check, I'm sure we're good. Okay. And in between, we have the LPO MSA activity. And the point I wanted to make is that LPO is not really a standalone specification. It's a specification that builds off of the OIF CEI linear spec. It changes a few things. It has a higher loss allowance, for instance. It allows up to 12 dB loss channel as opposed to the 9 dB that's in the OIS specification. And it also brings to the table a few revised optical specifications, all in line with hitting the lower power objective, notably lower laser power and optical extinction ratio properties. And then we also have the RTLR activity. This is the also sometimes known as a TRO, transmitter retimed only. This is also a relatively new newcomer, started in 2024. And its electrical interfaces are built more around the IEEE C to M type of interface as opposed to the VSR interconnects that we see in the linear space. Very good. We'll move ahead here. As Ed indicated, there have been some new measurements developed, and I wanted to offer a little bit of a high-level overview. So it's always best when you build on the measurement science and the techniques that have been established ahead of or before us, and basically improve what's worked well. And that's really probably the best way to describe some of these new measurements that are applied towards validation of these optical and linear eyes. Most of you are familiar with TDEQ. This is a penalty operation that's been in use for many years now, over a decade. And I provide a reference to the original Jonathan King contribution that led to TDEQ, and many contributors to that are long, can't be mentioned here. But we have the basically measures the amount of noise that can be added to an ideal receiver compared to an ideal unequalized transmitter, and that's represented as is a 10 log of the OMA of over 6Q over the random noise. And the random noise is the amount of noise you dial up to hit a BER or an SER of was it 2.4 e to the minus 5, I believe it is. or I'm sorry, 4.8 e to the minus 4. Ohma is a measurement that's basically the difference between the optical power between the levels of a PAM4 signal, and CEQ is the optical measurement that evaluates the noise gain through the TDEC equalizer. Again, all the optical measurements are represented as 10 log since it's optical power. Similarly, the EECQ, which was introduced in the OIF contribution back in 2021, the reference is provided here. It's similar to TDEC-Q, but it offers some insights into really the signal quality. It's meant to be an improvement or a build on vertical eye closure, or VEC. Now, CEQ really, or EECQ really gives you the ratio of the total signal strength to the net usable signal strength. And it does so because because it does not really incorporate the cost of the equalizing of the signal. It's not a true penalty measurement like TDEC-Q is. VMA is the electrical equivalent of OMA, similar to where we look at the voltage levels. And then CEQ is the electrical equivalent of CEQ. And CEQ reflects the quality of the optimization. And we have two key places where we have to measure CEQ. This is test point 1A at the beginning of the signal path, electrical signal path, and at the end of the electrical signal path at TP4. And the nature of the equalizers at these 2 points get progressively more complicated. Probably best illustrated in the next slide here. All right, CEQ here, you can see that CEQ in the case of TP1A, the equalizer to TP1A in the linear system here, OIF linear spec, is a 5-tap FFE, and the LPO MSA, it's a 9-tap FFE, but that doesn't matter. They have a CTLE, we have FFE, and we measure CEQ at the output of this point, same place where we do EECQ and VMA. It's after the sigma n, the noise injection point. The challenge here is that at test point 4 requires fairly careful co-optimization of both a CTLE, an FFE, and a DFE. And the DFE is a nonlinear operation. So it's important to be able to thread the CEQ operation in between your FFE and just before the DFE. You don't want to do a CEQ operation after a nonlinear operator. Part of the optimization strategy that we discussed a little bit earlier revolves around the tap structures. So we have 22 tap FFE, a DFE, and a CTLE, and it can be a bit of a challenge to get all these coefficients dialed in. Traditionally, we've used a pulse response technique where we would feed the pulse response measured at the respective test point along with the noise into COM, let COM back simulate all the different coefficients that give us the best figure of merit, and then we take those coefficients and put them back into the instrumentation. And until just recently, that was the standard state of the art in terms of how to do this operation. As of actually just last week, January 31st was the release date, version A7.80 firmware for the DCA, and it introduces this concept known as a co-optimization tool. This has been a tool that's been long in coming, and it reduces this roughly 20-minute process of extracting pulse response and going to COM and then taking coefficients back into your instrument into a 1-second button press now. And what it does is it really enables a person to get the right amount of energy into the DFE, which up to this point has been very hard to do without a simulation environment. If you see the typical way that you would tune an equalizer in a left to right configuration, you would optimize your linear FFE, and then you would pick up the residual equalization with your DFE, which is exactly opposite of how you want to do this. You want to utilize the DFE to its fullest capacity. You want to get as much energy into the DFE and then have the FFE before it, the TDEC-Q equalizer, pick up the difference. So this gives you an optimization solution that actually is nearly impossible to get by hand. It's possible to get to through simulation and COM. And now the this co-optimization operator that we have in the DCA firmware allows you to get there quite easily. All right. Let's talk a little bit about a couple of test points here for validation. I'll talk about test point 1A to start off, and a bit about the reference equalizer. Our reference receiver that we're using for TP1A is going to be a scope in this case. It's going to have a 42 gigahertz Bessel-Thompson response. We'll have a CTLE, and we'll have the FFE, the TDEC optimization that we use to do effectively the EECQ operation. Through the course of these slides, you will see us talk about TDECQ and EECQ at roughly the same level. As I cited in the slide earlier, we have 20 log. The difference in the noise injection ratio gives you an EECQ 10 log for optical power. If you take a TDECQ result, whether it's 2 dB or 3 dB, and you double it, you get the EECQ number. It's the electrical equivalent. It's just 2 times the optical version. We have the OICEI specification has a 5-tap equalizer or a 9-tap with the LPMSA specifications. We have a handy set of tables here that basically allow you to adjust your CTLE through a process of knowing what the channel losses are on your host. So there's a couple different loss configurations, short, medium, and long loss. And we would take those loss numbers and use that as a starting point to dial in the 2-pole or 2-gain stage equalizer for the CTLE. Okay, let me build this slide out here. So in this case here, we're going to talk about validating switches. And in these cases, we want to look at TP1A. This is the host output. Similarly, Hayden will talk about the host input stress test that goes on when we feed an impaired signal into these ports and gauge their performance. For the next slide, we'll talk about basically evaluating the long path, which is this red arc right here, a medium path, and a short path. And we see variations anywhere from about these signal paths here could range anywhere from 13, 14 dB to 3 dB on the very short side. All right. I will move quickly here into this slide. This gets into some of the details about TP1A. Here we have a host transmitter. We actually take it into, in this case, a sampling scope. It's a relatively straightforward measurement to do. For filter, the circ, we have basically a band pass or a filter system on our scope that gives you highly constrained roll-off conditions. An instrument by itself won't give you a Bessel-Thompson response, but we can condition the signal response digitally to give you 42 gigahertz Bessel or whatever bandwidth specification you need within the allowances of that hardware. We then implement the CTLE based on this table here on the right-hand side, and then we auto set the TDECQ to use an MMSC approach to give us the best coefficients in either the 5-tap or 9-tap for filter. After that, we would then proceed to perform your EECQ operation, which again is 2 times your TDECQ, the CEQ, and the VMA overshoot and undershoot operations. On the other hand, if you take it to the next test point over, that's test point 2. That's where we actually test a module. So assuming that your TP1A is at a reasonable stress level, you can then feed that electrical signal into the module, and you can gauge and grade the quality of the optical signal that's being broadcast by the device. And that would be test point 2, traditional TDECQ measurement. Standard measurements like OMA, optical extinction ratio, CEQ, over and undershoot, these are measurements that have been done for years on the optical path, and these are followed similarly here in the LPO MSA. The only thing that has to be taken into account are the impairments coming into the electrical side of this module, the calibration process associated with that, and the need to be able to cycle through different loss configurations. This gets done a couple different ways. We have a frequency-dependent attenuator here in this block. You can either use a trace board, Or in many cases, we just use the built-in FIR filters or that are built into the signal generator here to detune the signal to, in effect, synthesize the effects of a channel loss. And it does the same thing as an ISI board and allows you to cycle between the different ISI profiles. The calibration process that was used in the previous slide is illustrated here. We use, in this case here, we'd actually generate the signal. We'd go through our ISI board through the either the detuning process of the FIR filter on the generator or going through an FDA, through a mated test fixture here into the scope, go through and set up our filter structures here and calibrate our electrical properties to make sure that they satisfy TP1 criteria, EECQ, and all the other elements that are important for a minimally viable signal at TP1A. There's a couple ways to do this. You can have signals that are over strength, or you can have them right at the wire in terms of minimum amplitude. And all these are important to understand the performance and overdrive capabilities of these modules. All right, from here I'll hand it over to my colleague Hadrian.
Thank you very much, John. Yeah, so hello everyone. So I would like to start again from this nice LPO link overview. So going from one host to the other using two LPO modules. So John already covered the host input test at TP1A and the module input test between TP0 and TP2. And what I would like to do now is to discuss the module output test, so between TP3 and TP4, and the host input test between TP4A and TP5. So let's start with a module output test, and this is how a typical setup look like. So you have on the left side, the equipment required to generate optical stress signal at TP3. So it usually consists of a bird on a E to O converter and an optical scope. And you see that this stress signal is injected into the module, which is plugged into MCB, and the resulting electrical signal is captured at TP2. So the first thing to mention is that the stress signal calibration is similar to what is already defined in the IEEE, and is done using SSPRQ pattern. So what is the process of analyzing the TP4 signal? You first have your fourth order Bessel-Thomson response filter, which is generated using SIRC, so system input response. So John covered this part already. And use the reference receiver, then follows a CTLE follows. Sorry, this is a low pass response filter, and the CTLE should be set according to the loss of the test channel. So, and then we have the 22 taps FFE followed by 1 taps DFE that needs to be optimized, and John covered this already. And the EECQ and the VMA are measured at the output of this reference equalizer. So there are some slight differences between for the TP3 requirements between the CI 112G linear standards and the LPO MSA, but these are only details. The overall procedure and test procedure is similar. So this is how the test looks like. And before we go to have a look at typical results, I would like to discuss a bit the reference receiver. So John covered already the reference receiver at TP1A, and I would like to discuss the reference receiver at TP4. So as I said, it consists of a low-pass filter with 32 gigahertz bandwidth, followed by a 2-gain stage CTLE, 22 taps FFE, and 1 taps DFE. And the purpose of this architecture intends to emulate the equalizer of a LPO-capable host receiver. And when we look at this way, it actually emulate it assumes the use case of a short host signal, a short host channel. Sorry. So we are measuring the signal at the output of the MCB, which is equivalent to the short host channel scenario. Real equalizers, so real receiver, will have to equalize longer channels. So as John mentioned, up to 10 dB difference between the short host channel and the long host channel. And the key point here is really to co-optimize the CTLE, the 22 taps FFE and the 1 taps DFE. And this is a feature that has been discussed in the previous slides. So let me continue and discuss some typical results for TP3, TP4 measurements. So here on the left side, you see an optical stress signal at TP3. So it's a calibrated stress signal. So you can see the actual metrics of this signal in terms of outer OMA, outer extinction ratio, and TDECQ compared to the specs targets for LPO MSA. So you see that the actual measurements and the targets are very close to each other. So we can use this signal to stress our module. And now I would like to show you the resulting signal at TP4. So on the left side, so I forgot to mention this. So let me go back here. What you see, the orange waveform is basically the raw signal, while the green waveform is a signal after the 9 taps TDECQ. So it's the equalized signal that we use to measure the EECQ value. The TDECQ value, sorry. Now let's have a look at the resulting signal at TP4. The yellow waveform is actually the raw waveform at the TP4, just after the CTLE. It's where we measure the VMA. And the pink waveform is at the output of the reference equalizer. So after the 22 taps FFE and the DFE. And you see that both the VMA and the EECQ meet the specs limit. So in one case, we have 500 millivolt VMA, while the specs requires to have above 250 millivolt. And in terms of EECQ, we measured 4 dB, while the limit would be 6 dB. So here we have a compliant module. Another test that we can do to validate a module is a so-called TP5 module. It's a typical test. It's not mandatory, but it's basically measuring the resulting BR of this module using a compliant host. And so a compliant host could be any host that has been previously validated and find conformant to the specs. Or you can use also lab-grade equipment, such as an error detector together with a frequency-dependent attenuator to emulate medium and long channel. So in this case, TP5 measurements for module, what we are trying to measure is the BR and the FEC stats at the error detector. So for the BR, we are using a PRBS31Q, while for to find the FEC stats, we can use FEC encoded the scrambled idle pattern, for instance. So here is a typical results of TP5 measurements. What you can see on the left is basically the signal after the receiver equalizer. So here is just to check that the equalizer is actually capable of equalizing the signal. Here in the middle, you see the FEC error stats. So here described as a distribution of the number of error symbol per fake code words. And you also have the information about the raw bit error rate. So in all this case here, the FEC stats meet the LPO MSA standard, which expect to be which expect not to have more than 6 error bins per code words, and the BR target would be 1 to the minus 6. So we are well below this limits here. So let's now move to the host testing part. Here, this is how a typical setup would look like. So you see the bird on the left generating the stress signal, and which is being injected into the host with a host compliance board. It's important to note that the calibrated stress the stress signal should be calibrated for 2 cases: the short and long host channel. And if you have medium channel on your host, then it should be tested using both short and long stress signals. The criteria for the host input test is a jitter tolerance. So basically measuring the BR for different amplitude and frequency of the sinusoidal jitter, and changing this jitter according to a jitter profile defined in the OFCI specs. So, but before we need to calibrate this stress signal, and here there are a different approach depending if you're following the CI 112G linear or the LPO MSA. You can reach out to me, or we can discuss this later in the webinar if you're interested into this difference. But the high-level procedure would be to calibrate the stress signal using a PRBS13Q, adjust the CTLE depending on the mated test fixture loss. So your calibration channel is a mated test fixture, and to adjust the pattern generator amplitude and the stress component to meet your EECQ and VMA at the end of the reference receiver. So here I would like to dig into the detailed calibration process. So I'm doing this for the LPO MSA, and this calibration process is subjected to change because, as Sean mentioned at the beginning, there is a plugfest right now where this procedure is being tested and validated. But okay, let's try it with the current procedure. You start with a pattern generator without DN phases, and then you start to inject 10 milli random jitter and 50 milli SJ. You usually inject this sinusoidal jitter at high frequency so that it goes through your clock recovery loop bandwidth and can be captured on the scope. You then inject broadband noise. This broadband noise should be calibrated at TP4. It basically emulates or stands for the noise generated by the TIA in your module. You inject twice as much broadband noise for the long host calibration channel as for the short, because the long host, the calibration for the long host has twice as much as amplitude. So the idea is to get to have the same SNR for both cases. And then you start to measure the VMA and EECQ at the output of your reference receiver on the scope. You then adjust the PG amplitude toward the VMA targets, so different for the short or long host channel. And then if your EECQ is still too low, you start to detune the pattern, the FIR, so the DN phases of your coefficient of your pattern generator, or equivalently to add some ISI into your test channel to degrade the signal. And then you optimize again your reference receiver to accommodate for the new channel. And this is an iterative process. And you continue this process until you reach the desired VMA and EECQ at TP4. So once you have a calibrated signal like shown on the screen, you can see the yellow waveform is a raw signal, so measured at TP4, and the pink one is at the end of the reference equalizer. This stress signal meet the specs target that are 500 millivolt VMA and 6 dB EECQ. So this is the signal we will use to test our host. And these are typical results for the host. So here I've listed both CI112G linear and LPO MSA approach. They are very similar, but they differ in terms of slightly differ in terms of targets. So first of all, both of them are looking at taking the BR as a metric. For 112G linear, it's 2 to the -4 prefec, while for LPO MSA, it's 1 to the -6. They also both consider the post-FEC performance of the system of the host. LPO MSA considering the FLR, while the post OFCI is considering the post-FEC BR, but these two are equivalent. And there is an additional metric that has been introduced in the LPO MSA, which is the maximum number of FEC bins that are measured after 100 seconds. So this is to ensure that your host has enough FEC margin to operate. So in this particular case, this particular host, after 100 seconds, we could measure some code words with 8 symbol errors. And therefore, this particular host would meet the LPO MSA requirements. So this is all I wanted to discuss today. So I'm handing over back to you, Sean. Thank you.
Very good. No, thank you everyone for again for a great presentation here. Lots of I'm sure there's going to be lots of excitement, and especially be curious to see how the Plug Fest goes, which I'm sure more details will come out about that later. But yeah, great. All right, let's get to some questions here. Let's start with this one. If OIF linear addresses the market need, why is there an LPO MSA separate from the OIF spec? That's probably be good to know that. Yeah. Who wants to grab that one?
Sure, I can talk about that one. So basically, as I kind of alluded to in the introductory slides, so OIF has done a really good job on the baseline specification. LPO MSA picked it up. You could see on the one chart the host lost host ball to the electronics in the LPO module is 13 dB. LPO MSA was interested in increasing that loss to 16 dB. So 16 dB is kind of the number that everyone uses for chip to module or VSR. So there's a slight tweak. The methodology that OIF invented and that's been accepted by the industry is identical. And what happens is LPO MSA took that and they tweaked it to get the extra few dB to get to VSR length. And then on the optical side, there was also if you were to just clone the IEEE spec for single mode DR4, you can actually you could use that, but you can also do some power savings if you can drop the extinction ratio a little bit. So people that determined that you could drop the extinction ratio from what's in the IEEE spec down. So there's some savings on that point, and you could drop the optical power down. So it's really a solution that's kind of been, again, really optimized for low power. And so the industry decided that for single mode, they really want a very optimized power solution, and that kind of started the LPO MSA. So LPO MSA will be looking at also future PMDs and future speeds as well.
Great. Yeah, no, definitely. It's the OIF is doing some great things, and probably we'll hear more as OFC approaches. Here's an interesting question. What specific diagnostic functions can a hyperscale operator use in an LPO when a link fails? Certainly lots of activity with hyperscalers and AI, but if anybody wants to take that one on, yeah.
I can take a crack at that. I mean, you can have a link performance in a link BER that is going to be the first indication that you're not properly tuned. And true enough, I mean, getting a well-tuned link is actually one of the challenges that's in front of the whole linear technology group here. The demarcation point that Ed had alluded to in his material where you retime at the chip to module interfaces, has been a convenient spot to reset your electrical properties. So it left a lot of margin, a lot of opportunity for mistuned systems to still operate well. That doesn't exist in linear systems. You really have to have the tuning down very, very well. You have to, and there's a tuning process which we alluded to here. And if you're looking at BER or SER, basically your post-FEC TC or tail performance is an indicator that most SerDes receivers have to indicate what the error stats are and whether or not a retuning is required or not. And I wanted to further add to this, though. While this is actually one of the challenges that's in front of the 112 gig linear community today, it's going to be before everybody as we go to 200 gigabits per second. 200 gigabits per second is going to require similar attention to this tuning, even for things like chip to module. The loss numbers are very profound at 200 gigabits per second. So if you're accustomed to having the additional margin, making things work, that is traditional with a retime system, you're going to have to make very, very tight adjustments here on terms of your link performance and your tuning when you go to 200 gig, similar to what we're doing right now. And the primary metric is going to be FLR.
Great. Okay. Let's see. I'll take another one here. With signal processing moving into the platforms, don't they require increased power consumption to handle the additional signal processing?
Sure, I can take that one. So what one fact I didn't mention in the introduction slides was that actually when the 112 gig linear project was started in OIF, more or less it cloned the existing host capabilities. So the transmitter FIR that you see in VSR or chip to module on the transmit side and the host is the same for LPO MSA. The receiver with the 22 tap FFE, that's the same. So more or less a host, a company manufacturing host switches doesn't really have to say, oh, I need to build a different kind of equalization function into a switch that's going to talk to an LPO module. You're leveraging the same equalization that you have today in what you would need for a VSR link or for other links like KR, IEEE backplane or whatever. So that's already been it's all preserved. So there's not really any significant increase in power on the host side, just because you're driving now an LPO module instead of a retime module.
Okay. I'm just going to keep jumping around here. Does the linear module imply the TIA should be more or less comparable to typical module SerDes, TX in drive strength, FFE, tap, etc.? If so, will these things result in more consumption to that TIA? That's another lot of stuff there to unpack, I guess.
Yeah, maybe we don't have the time to go into all the details, but basically,
yeah,
you can. Yeah, I can give just a high-level answer that the TIA in essence is the TIA that would go inside a retime module on the receiver would be pretty much the same as the TIA that would go into an LPO module. The one kind of thing that is important, I agree, and that's kind of covered by this specification, is the output signal swing. So for a long channel, I kind of alluded on the one slide that OIF has seen this document for module management and a VCS document. And so those documents outline how the module is controlled by the host. And so for a short channel, you might not need so much swing coming out of the LPO module, so you can dial down the output swing from the TIA back into the host. Or for a long channel, you could increase the swing to maybe 500 or 600 millivolts instead of 300 millivolts. So that's kind of left at the discretion of the switch implementer, how he wants to deal with LPO modules, and when he's aware whether they're being applied to a short electrical link or a long electrical link. In terms of the one aspect, there is a CTLE function within the TIA as well. So the TIA can have some peaking on its output and that is also provisioned for in the OIF, in the CMIS and the DCS documents. So I don't think we have time to get into that today, but yeah.
Right. Yeah, but different options, I guess, is what you're saying, depending on the situation, I suppose. Yeah. Okay, got it. There's another question here. We got time for a few more. You mentioned that the host input test procedures between CEI 112G linear and LPO MSA are different. Can you elaborate on that a little bit? Maybe Hadrian.
I can take this. Yes.
Yeah.
So, so the LPO MSA work group identify the need to have a more realistic stress signal for the host input test. The reason for this is that the OIF CI 112G linear specs is more or less leveraging the existing specification and test procedure for VSR, which is a retimed interface. And the way to stress this interface is to inject a lot of jitter. And this is not very realistic to what comes out of an LPO module. In the LPO module, you have more a very distorted signal with a significant amount of random noise. And this is why the LPO MSA slightly modified this the testing, the host input test procedure, just to be more realistic, to stick to the to the LPO use case.
Okay, great. I think we got time maybe for like one more question, some wrap up here. This question is, what is the need for 22 tap FFE at host RX? Does this mean host RX should be capable enough to support LPO? I guess a lot of questions around those. Yeah. Who wants to grab that one?
I can say a comment on that one, sure. So it kind of again alludes to what I was saying, is that the LPO, the host switch, as much as possible, it actually doesn't require some upgraded capability. So that is kind of, if people look into the VSR or chip to module spec, you'll see that that more or less is a clone of the capability that we have today in the switch CERTAS. So that 22 tap FFE, 1 tap DFE capability is there today in the switches.
Okay, great. Well, we're just about out of time, but if I could just have each of you just take like 30 seconds, just give me some final thoughts, and we can wrap up the webinar. I guess, whoever wants to start, Ed or Hadrian,
sure,
anybody, just
sure.
Real quick.
So hopefully we gave you a good intro, and I think the one message from me is that the industry's worked hard on this. We've all worked hard on this. John, Hadrian, myself, a lot of industry partners. I think we're at the point where the systems are robust, and we have a means now to verify in actual production for stress module testing. We have a very solid path forward, and so I think the message is basically that the industry has options now. If you want to go full retime, you want to go RTLR half retime, there will be options for the industry. And if you want to go LPO, there will be options for pluggable. And as well, LPO, it's not just about pluggable, it's also about near packaged optics, co-packaged optics. So at 224 gig, I mentioned there was a VSR, a linear project. So that will likely get leveraged for co-packaged optics, for instance. Yeah.
Great, another great topic. And Hadrian and John, if you want to just give a quick some quick final thoughts. Yeah,
Sean, I just wanted to say that, from the get-go, the linear project was faced with kind of an identity crisis, which was, if you take the retimers out, will it work? And that concern early on actually led to, the most significant interoperability program here in the Ethernet space, in the OIF space today. Traditionally, there hasn't been a huge amount of interoperability across the industry, and the kind of events that are going on today and have gone on in previous months as well have brought together systems and cable vendors really for the first time here in an interoperability focused setting. So it's helped the community, it's made the ecosystem better, more powerful players, and we now actually know that interoperability can be achieved through some of these careful control in the settings of transmitter properties, receiver properties, and various SerDes designs.
Great. Adrian, you want to just give a couple quick final thoughts and we can wrap up. Yeah.
Oh, I just wanted to say I can't wait for the next Plugfest, looking at the next generation of LPO
Nice.
working at 224G. So
Great.
this will be great.
No, it sounds like everybody's making some great progress. That's good news to hear, and I look forward to maybe catching up with all of you, maybe at OFC. Certainly, this will probably be a hot topic there, like it was last year. I know it's still sort of like getting out of the gate, but again, thanks to all the three great speakers, Hadrian, John, and Ed, for coming here today, and again to our sponsor Keysight. I think this was a great discussion. Sounds like maybe we could have more webinars related to this, because I think there's a lot of things to explore. But thanks very much, everybody, and to the audience. Have a great afternoon, and we hope to see you soon in another webinar. Thanks again. Thank you. Bye-bye.
Thanks, everybody.
Thank you, everybody.